In this module, we explore the serviceability of bending members. Beams are the most common types of elements that engineers have to get involved with designing. We look at the serviceability limit state. We'll look at deflection limits and the way in which engineers model the deflection of beams, including creep deflections using J2. We'll finish off with a worked example. The serviceability limit state is about performance on an everyday basis. When we design for the strength limit state, we're interested in avoiding failure. But when we're looking at the serviceability limit state, we're asking ourselves, will this member deflect too much or bounce too much? So it's this kind of appearance that we're trying to avoid. Typically, we're using everyday loads. In structural terms, we're using loads with a high return period. Typically, the serviceability limit state uses loads that have got a 1 in 20 probability of exceedance in any 1 year. Every time we look at the serviceability limit state, we're trying to limit a serviceability performance, a deflection or a vibration. So there has to be a deflection limit or a vibration limit. And we're going to essentially model it with elastic behaviour because we are modelling elastic response of the structure. Often the serviceability limit state does govern the design of bending members, but particularly if the member is a long span and lightly loaded, typical of floors and roof structures. So serviceability of beams. The beam deflection can be limited for a number of different reasons. It could be appearance. Sometimes looking along a structure, you'll look along a sight line. And if the structure is deflecting too much, you will see a curve in that sight line, and the architect will want to avoid that. So there will be an appearance limit. Other times we'll be interested in how bouncy is a floor. So often floors are limited by vibration deflection limits. And sometimes if something sags too much, it can lead to unintended load paths. A classic is if a lintel over the top of a window deflects so much that it hits the top of the window, then it transfers loads directly into the window and can cause the window to break. So their deflection could lead to structural damage to the building. That's an unintended structural load path. And finally, function can be affected by deflection. If a beam over the top of a door deflects too much, it can hit the top of the door and prevent the door from opening. And that again is a serviceability failure. They're the things that we're trying to avoid in checking the serviceability of members. Now, the Australian standard gives us guidance on checking serviceability. There are no hard and fast serviceability limits. Limits are agreed with the client. And some buildings will have really tight serviceability limits and others will have fairly generous serviceability limits. In some cases, serviceability limits have to be tight because of the function of the building. For example, if you're designing beams underneath some rotating machinery and that beam deflects too much, it can cause the rotating machinery to malfunction. And so there, that beam would have a very tight deflection limit. In other cases, it doesn't matter too much whether the beam deflects too much. And this is typical of roofs, where we can accommodate a little bit of deflection in the roof without causing any structural problems at all. So serviceability limits are set between the designer and the client, and they take into account what is the consequence of the deflection. If it deflects too much, what goes wrong? The load that is actually applied, what are we modelling in thinking about this deflection limit? And then there's the limit itself. So limits are variable. Duration of load is something that also has to be modelled with some materials. Timber and concrete show deflection over a period of time. We call it creep. And there is a video available on creep deflection of timber that does outline why the creep actually occurs. But we model it by using an elastic equation with a multiplier. And that multiplier is larger if the load is applied over a longer period of time. That multiplier is the J2 factor. The J2 factor does vary according to the moisture content of the timber. The higher the moisture content of the timber, the more prone the timber is to having this creep deflection, which is deflection after the load has been put on. So for long duration loads, we multiply the elastic deflection by a higher number to model that creep deflection. So in summary, we have an elastic deflection equation that we modify using a factor J2 to take account of its creep. We'll illustrate it with a worked example. And this is a worked example of a floor system. And a floor system makes use of a number of floor joists. So here is a model showing a large number of floor joists working together. And as a load is applied, an out-of-plane load is applied to the floor, each of these floor joists cooperate in resisting that load, so that the deflection of the floor system is given by the performance of all of the floor joists in the system. The average modulus of elasticity is the one that's totally appropriate for us to use, and we're using MGP10 timber. MGP10 timber has got a modulus of elasticity of 10,000 megapascals. Okay, so that we've got a span of about 2.65 metres for these, and the floor joists are 140 by 45, so that they're that size. The serviceability check is required to look at some specific load cases, and there are 3 load cases given here. In these load cases, we're going to be looking at the deflection of the timber members under the action of imposed loads alone. So as the imposed loads are applied, how much extra deflection is experienced by the floor itself. Then we'll look at the case where underneath one particular floor joist is a partition. And if that floor joist deflects too much, it's going to damage that partition. And its total deflection is important, so it's a combination of the imposed load and the permanent load on the joist, the sum of all of the loads on that particular joist, and we want to avoid damage to that partition. And finally, often for floors, we're worried about bounce. How bouncy is the floor? And there's an empirical rule for determining the bounciness of the floor, and that is how much does it deflect under a 1 kilonewton applied point load in the centre of the floor. So we're going to look at the performance of the floor under each of those load cases. So the design action, the imposed load from a crowd, is going to be the first load case. So it's only the imposed load, and we're going to calculate on the floor joists the deflection under that load using an average modulus of elasticity. We can calculate the load on it as 1.26 kilonewtons per metre length of floor joist, and then the deflection under that short-term imposed action. Now, this is where the duration of load is important. If we're thinking about crowd loads, crowds don't stay on a load on the floor for a long period of time, certainly not more than a year. They're on for less than a day. So that's classified as a short-term load, and the J2 factor is 1 for that. So we're using J2 equals 1, and then we're applying the normal elastic deflection equation for a uniformly distributed load over a simply supported span, using 10,000 as the modulus of elasticity. We find that the deflection is 7.86 millimetres, which is less than our limiting deflection, which was span divided by 300. So that joist satisfies that particular load case. The imposed and permanent combination, that was the one where we're looking at avoiding failure of a partition under one particular floor joist. In this case, it's not the modulus of elasticity of all of the floor joists that we're concerned about. It's just the modulus of elasticity of this floor joist over the top of the partition. So for that particular floor joist, we're going to use a 5th percentile estimate. That way we'll always be conservative. So we're not using 10,000 megapascals. We'll use the modulus of elasticity that we estimate to be the 5th percentile for this product, and that's 7,000 megapascals. Now, we're looking at a combination of permanent action and imposed action. so that the duration of the permanent action is long term. It's going to be there forever. And so the J2 factor is going to be appropriate for the long-term component. So for the permanent action, we're looking at a J2 of 2. And for the imposed action, which again is a crowd load, it's a short duration load. We're using a different J2. We're using 1 for the imposed action. We find the two deflections, add them together. Is it less than the clearance over the top of the partition? It is, so we've satisfied that serviceability check. Finally, there is the 1 kilonewton point load in the middle of the floor. Now, if we apply a load to one floor joist, the crossing members, in this case the floor, is going to transfer some of that load to others. We can do a calculation to determine how much load is going to find its way into one particular floor joist, and that is a G41 factor. And that G41 factor is calculated using the relative stiffness of the floor joists and the crossing members. In this case, we find that the G41 factor is 0.376, so 37.6% of that 1 kilonewton point load is going to find its way into one floor joist. We then apply that load to one floor joist and calculate its deflection. This time, because it's a point load, we're using a different expression. We're not using the uniformly distributed load case, we're using the point load case, using the calculation for its deflection under a short-term load. We find 1.42 millimetres. Again, it's less than the serviceability limit of 2 millimetres. So 3 different load cases, 3 serviceability checks. It passes all of them, so it is satisfactory in its serviceability performance. In summary, the serviceability limit state can be critical for some members. Typically, they're long span members and lightly loaded members. The deflection limits are not going to apply to everything, but they are going to apply to some specific members, and they take into account consequence, the load that's applied, and the limit on the deflection that is required. Creep has to be modelled for long duration loads, and long duration loads are going to have a J2 factor that models the creep performance.